All right, let's get started. Hello, everyone. My name is Szilard. I am the organizer of this meetup. And today we'll continue with another talk on gradient boosting.
Hi, everyone.
Last time, some of you might have attended. Last two times we had the lead maintainer of XGBoost, and last time we had core developer of LightGBM. And today we have a talk about CatBoost. Our speaker is Stanislav Kirillov. He is the head of CatBoost development team at Yandex. Thank you, Stan, for coming and talking to our meetup.
Yes, hi everyone.
He's not only the head of the team, but he's very hands-on. He's one of the persons who has the most commits in the GitHub repo. That's why I invited him to talk, because I think he is the most qualified person to talk about CatBoost. So welcome to our meetup, and I will turn off the slide share, and then you can start the talk.
So let's begin. My name is Stanislav Kirillov, and I'm the head of CatBoost and ML systems group at Yandex. We develop different machine learning tools, and we are developing lots of ML infrastructure tools for training different kind of models. But one of the most time-consuming and one of my favorite job, one of the main parts of my job is developing CatBoost. And today we are going to talk about
how do we convey we're not disheveled over the phone? Well, on the phone, it does.
I was muted, yes. Okay, so my name is Stanislav Kirillov, and I'm head of machine learning systems group at Yandex. In Yandex, Yandex is a big information technology company in Russia, and we develop different services like web search, image search, taxi service, ride sharing service. We are developing autonomous rovers and so on. And today I'm going to talk about a core instrument for doing machine learning in Yandex. It is CatBoost, and we are going to discuss distributed training, uncertainty estimation, and other news, and also core concepts of CatBoost and core features of CatBoost. So today's talk plan is to give you an introduction about CatBoost, to discuss main features of CatBoost, to talk about GPU support, about single host and distributed training, to present you CatBoost for Apache Spark, to talk about uncertainty estimation support in CatBoost, and to explain our further plans for CatBoost development. First of all, our development team is not so big, but we have 7 persons now in a core development team, and we are all doing some part of CatBoost. And so, first of all, what is CatBoost? CatBoost is a machine learning algorithm that uses gradient boosted or decision trees to build high-quality models. And we will briefly recall the basics of gradient boosting decision trees models, and in the next few slides. CatBoost is available as an open source library with Apache 2 license, so CatBoost is free, and I think that it's not only open source, but it's really easy to use, because all our functionality is available just like a pip install, or if you install our packet from CondaForge or from our GitHub releases page. So next slide. Why should you consider trying to use CatBoost? because CatBoost is one of the best gradient boosting decision trees libraries like LightBEM, XGBoost or H2O, and CatBoost has outstanding features. Like we have sophisticated feature type support. We support categorical features. We support text features, and now in experimental mode we support embedding features. Also, CatBoost has a really good quality when it is trained with default parameters, because we have done lots of work to make them really nice, and we have some heuristics to substitute proper default parameters looking at the dataset. For example, we are substituting after learning rate parameter. Also, CatBoost supports multiple tree grow policies. We support symmetric trees, which we will discuss later. We support loss guide and depth-wise trees. Also, CatBoost has a fast applier for its models, written mostly in C++ with simple instruction multi-data optimizations. Also, CatBoost have lots of nice features like model analysis tools, training process visualization, and also we have a novel uncertainty estimation support. Now let me discuss main features and concepts of CatBoost and gradient boosting. So first of all, main idea of training decision tree models is to select the best split and to add it to your tree. And the best split is some condition that splits your objects into two parts. And by best split, we mean that split divides objects into parts that such a division gives you the best loss function estimation gain. For example, information gain, and then you are repeating the task, splitting each new leaf into parts until the stopping criterion met. For example, the depth or the number of leaves. And then training continues. After we built one tree, we are starting building the next tree from scratch. And if we are building loss-guided trees, we add only one split with the biggest score to one of the leaves of the current tree. And when we are building trees with depth-wise strategy, we are trying to fill each level of a tree with a new split until, for example, mean data in leaves criterion achieved, and we don't want to split this leaf anymore. And selecting and scoring such splits could be a hard task, because if we are using greedy approach and we don't have something like prequantization or something, you have to try all possible splits for each feature to select the best split. And scanning through all the value through all the possible splits could be a really time-consuming task. So to avoid that, we can apply quantization and split objects into some buckets, and we can somehow optimize, optimally choose those splits to, for example, minimize some entropy of objects in those buckets. And after doing quantization, we can easily build derivatives histograms for those buckets. And then after aggregation of derivatives, we can easily calculate our estimated split loss function. Okay, so when you are using general purpose processors like x86-64, there is some tricks that you can do to make building those histograms faster. For example, you can try doing that in parallel, or try utilizing single instruction, multiple data instructions. And using this approach on GPU can give you even more speed up. And now it's time to know that CatBoost uses another tree structure building strategy by default. It uses so-called symmetric, or as we also name them, oblivious trees. Such trees are built layer by layer, but on some layer, all the conditions are the same. And that is displayed on the right side of the slide, the example of such tree. And those tree models are oblivious because the order of conditions in that tree doesn't really matter, because it only matters on the indices of leaves, but not on the values of those trees or objects in those leaves. Or only on leaf order, of course. And that structure leads to more generalized models. And of course, it's not good for any data, but for data with lots of features and for data with when features are not deeply linked between them, or there is no some inner correlations between those features, the oblivious trees could give you really nice results, and they have one really nice consequence. They don't overfit too fast. And another good outcome of using symmetric trees is that they are blazingly fast in inference, because a path in such tree is a simple binary vector, and so you can also build it with single instruction, multiple data instructions, or with GPUs, and you don't have some conditional jumps or something to do in your code. Another outstanding CatBoost feature is categorical feature support. Gradient boosting needs to build binary splits, and in binary splits we're using binary predicate functions, and there is no some default or always working way to do such splits. For example, classical approach is to use one-hot encoding, where you are using 0 or 1 for each unique value in for some categorical feature. And let me just recall what is categorical feature for just in case. Categorical features are the features that took only one value out of some predefined set of values. For example, it could be a music genre or artist name. For some musical composition, you can only mark only one artist or one genre. Of course, there could be multi-categorical features or multi-categorical, but categories are always the singular one. And using one-hot encoding is a simple and efficient technique, but it works really nice when you have not so much unique values of those categorical features, or when, another saying, when feature cardinality is low. In reality, many categorical features has a huge number of different values. As a result, it's hard to build an ensemble of decision trees with help of this technique. So to work with such features, one usually makes some value engineering instead of one-hot encoding. And feature engineering is regularly based on problem domain knowledge. And in CatBoost, we are using some knowledge from solving a task of showing or not showing advertisement banners in our Yandex advertisement networks. And it's called click-through rate or statistics for some category. And such statistics could use or not use labels of objects. Such category encodings could, if they are not doing in the right way, can lead to target leakage. And in CatBoost, we are using online approach to build build such counters. What do I mean? For every sample, we are using only data of from the object that was behind him in some permutation. And in this slide, you can see an example of calculating frequency of label equal to 1 for category SDE. And of course, it's important not only to calculate those statistics, it's also important to choose proper prior for values that you don't see before. So when you are building those categories, you can try different priors and select the best one for that feature. Another great example of inside feature processing in CatBoost is support for text features. CatBoost can handle normalized texts because we don't have inside lemmatizing engine. But if you somehow normalize your text, you can easily feed it into CatBoost. Then we can build different types of dictionaries. We can use simple token dictionaries. We can use multi-token dictionaries. For example, we can use n-grams. And CatBoost also has support for byte pair encoding. And after that, we have identifiers of tokens, and we can use them to calculate some different features. For example, we can calculate BM25 or term frequency, inverted document frequency, like features when we are trying to calculate the relevance of current text to the corpus of seen text in some class. Another approach is to train naive bias statistics or naive bias probabilities for some class, and then match the current text tokens with those probabilities, and to calculate the probability of these text being some of those classes. Another approach is pretty classic. It is when you are just building bag of words out of the tokenized text and replacing this text with zeros and ones sparse matrix. And all this gives pretty nice results. For example, there is a mixed feature dataset, rows and tomatoes, where there is numerical features, categorical features, and text descriptions to films. And using inside inner text processing possibilities in CatBoost can give you some 1 or 2% accuracy improvement just without any parameter tuning, just with adding some texts. Also, CatBoost supports object embeddings, and it is pretty experimental feature. What is object embeddings? Object embeddings is some mapping of object into vector space, and it is quite a classic approach now when you are training some convolutional neural networks or training some BERTs or GPT-like models, where you can use the latent vector as object embedding. And it is also it is always a hard task to make a bridge between neural network models and, for example, if you have a big and really nicely established pipeline with gradient boosting models, and you just want to have a bump of quality with using of some kind of neural networks. So now you can try using our embedding support. And how it is done inside. Inside, we have two different featurization algorithms. We use linear discriminant analysis, and we use k nearest neighbors mapping to to transform those high dimensionality vectors into some low dimensional subspace of features. And when we're speaking about linear discriminant analysis, it is pretty classic algorithm that tries to find a linear projection that maximally separate objects of different classes. On this slide, there is a simple illustration of such projection. For example, LD1 projection nicely separates the objects of red and blue classes. And another approach is to build a KNN index, for example, using HNSV or hierarchical navigable small world index, so you can easily find some nearest neighbors for an object and use the statistics of classes in those neighborhood to make it as to use it as a feature. And of course, we are using our online approach to build those features, saying that we have some permutations of objects in our data sets. We are making by default 3 different permutations, and then we are gradually training the LDA, and we are gradually building KNN index. And for some object, we are using a previous state of index of LDA formula. And all those give a pretty complicated image of CatBoost, because we have to somehow transform our, for example, text or categorical features into floating representation. Then we need to quantize them to make to make them available for our histograms building mechanism, and to make them make the processing faster. We need to build exclusive feature bundles like GBM to pack as much features as it's possible in one byte. And then we are, and moreover, in train loop, main train loop, we are greedily trying to combine different categorical features with different features that were met in the tree to try achieve even more quality of such representations. And when you have so more features or lots of data, you always thinking about using some GPU or something like that to process those data. And of course, CatBoost supports using GPUs for training and for inference. This slide presents performance results of training 1,000 of trees on Tesla V100 and on 3 classical data sets, Higgs, Epsilon, and Airlines. And as you see, CatBoost works really fast and nice when data sets has lots of floating only features. And when you have some categorical features, the training time could increase. And it increases because as I've said, we are trying to build greedy feature combinations, and you can easily shut it off by setting max CTR complexity to 1. So we won't try to combine any categorical features with any other features. And when you are training CatBoost on a single GPU, it's easy to do. When you have multiple GPUs in your machine, even such a setup internally in CatBoost is treated like a distributed training. And for such a training, we have two different schemes to do a data split between the nodes. First is document parallel when dataset is split by rows, and feature parallel when dataset is split by feature column blocks. And then each GPU computes its histograms part, and we are using one of two different histograms reduction scheme to calculate the feature split score. Also, we are supporting multi-host, multi-GPU training, and this scheme expands the multi-host training with help of OpenMPI library. So current limitation of using OpenMPI with CatBoost and GPUs is that you have to store all your data on the rank 0 device, and it's not so handy, or maybe it's not so easy to do. So we are working on making it easier, but there is no currently estimated time of arrival of making it easy. Also, we have multi-host. To try this feature, you have to build CatBoost from scratch from GitHub with setting minus D use MPI flag, and it will build MPI aware version of CatBoost. And you can have a question: what is the cost of such distributed training? To answer it, we've tried it into two different settings. We all those settings used V100 Tesla cards and our internal datasets for training ranking models, because the open source datasets are not big enough to fully utilize the network and to show the scalability problems, or maybe they are too small to fully show the latency of network. And first step, use old 1 gigabit network, the second InfiniBand network. And you can see that while we are experiencing slowdown due to network throughput and latency, it's not critical when you have lots of data. And if you have InfiniBand, you experience near zero slowdown and close to 2x speed up when you are adding 2x GPUs in your training setup. And now let me present a novel feature of CatBoost. It is CatBoost for Apache Spark. Why we developed CatBoost for Apache Spark? First of all, when we are talking about really big data, you have you need to have some way to train on them. And if your data don't fit in the memory of single host, you have to somehow start distributed training. And another one reason is that distributed training can give you a speed up, because when you have lots of data on single host, the communication cost, if you have too much data, could be less than speed up profit. And also, if you have also preset Spark cluster, or if you need flexibility of working with data on Spark, you can use CatBoost for Apache Spark. And another reason is that low-level data processing in Spark is faster than in Python, and that's pretty nice reason to use Spark. Another nice feature of CatBoost for Spark is that we support both Java or Scala and PySpark interfaces for CatBoost training on Spark clusters. And of course, our API is fully compatible with the Spark ML library. And here on slide, you can see a small example of starting CatBoost training on Spark. Here we can see creating a Spark session, loading dataset, creating a classifier, and feeding it on your data and predicting on cluster. And here we prepared comparison of CatBoost versus LightGBM and XGBoost on Spark. First, CatBoost currently don't support GPU training on Spark, but we are planning to make it available until the end of 2021. Also, CatBoost supports the scheme of counters calculation that I've mentioned before directly on Spark clusters. So it is it's a good possibility for you. Also, CatBoost has a novel pairwise training losses that are widely used inside Yandex, and I think it could be useful in your tasks. And pairwise training is when you have some pairwise markup for objects. For example, for some object, you can say that it is better or better than some other object. And for those pairwise classification, you can use CatBoost on Spark on your big data. Also, CatBoost supports prequantization of your data. So you don't need to quantize your data multi-times when you are, for example, just tuning parameters that don't involve of training, or don't involve quantization settings. Also, CatBoost supports PySpark, as I've said, but currently CatBoost don't support CatBoost Spark R. And here you can see speed benchmarks of CatBoost training on 3 different data sets, on Gridtail, Higgs, and Epsilon. And you can see that in this cluster configuration, when we have 16 nodes and each node have 16 cores, CatBoost works pretty nice in such a configuration, and I think that you can try it on your data and have a nice result. Another great feature of CatBoost, as I believe, is possibility to predict the uncertainty of estimated labels. What do I mean? In many fields, you have not only predict some label or some value, you also need to predict a confidence of model in on that object. For example, when you are predicting some diagnosis, or you are predicting some financial or credit data which involves high risk, you need to know whether you can trust this prediction or not. And we've supported 2 different kinds of uncertainty estimation. First of all, first example is data uncertainty. And by data uncertainty, we mean that uncertainty that is built in your data, that is mixed in your data. For example, the noise in labels, or some noise in one feature, or something like that. And to estimate uncertainty for classification models, you can just use an entropy of predicted probability. But for regression models, there were no some good approach until natural gradient boosting by Andrew Ng appeared. This loss function is and approach is available like a RMSE with uncertainty in CatBoost library. And inside it works like a mix of RMSE and MLL losses, in which one component predicts the value, and the second component predicts the standard deviation of that value. And on the slide, you can show a small toy example of single dimension regression when we have an X as a feature and Y as a label. And here, gray dots are objects you need to predict on, and blue line is predicted value, and orange line is predicted deviation, or in that case, data uncertainty. Another uncertainty is knowledge uncertainty, and it comes from model uncertainty, that when you're training different models, each with different seeds, for example, each model can give some different results. And to estimate the knowledge of uncertainty of models, you can use an ensemble of pre-trained models, for example, with different seeds. And building, so for example, 10 different models could be costly in matters of time. So we are using a new approach of uncertainty estimation with virtual ensembles. We've published a paper about this approach, and inside it works like that. We are using Langevin dynamics boosting to add some noise to gradients and to leaf values. We are shrinking model, constantly shrinking model. So such models has some property that we can cut any subset starting from 0 tree and to some point of tree, and we can unshrink model prediction value, and such unshrinked value is good enough to make uncertainty predictions. And here is an example of knowledge uncertainty prediction. Here I am using the same toy sample data set of single dimensional regression. And here you can see the magenta line is a predicted value, and the blue line is a predicted knowledge uncertainty. And you can see that in the range where there were no training samples, the knowledge uncertainty is pretty high, and you can use this to somehow, for example, send data to labeling or somehow work with that cases. Another new feature is support of recursive feature elimination for selecting from hundreds and thousands of feature candidates, where it can be useful. Inside in Yandex, we have lots of ideas, and for new features. And it's a really hard task to select some subset of good features out of thousands of features candidates. And we are using recursive feature elimination like in scikit-learn, but we are reusing the preprocessed and prequantized data inside, so we can save time for retraining the models without some feature subset. And if you're interested in this, we can discuss it later. It's a pretty new feature. And to visualize it, we have some built-in visualization for that process. And based on sharp value predictions, we can estimate the model value without some feature, and then measure loss value of the model without that feature. And here on that graph, you can see the red dots that are the actual trained model loss values, and the green line, green dots are loss function values approximated by sharp values estimation. Also, CatBoost has lots of different tools to work with models. For example, we have per feature model analysis chart shown on the right of this slide. We have different types of feature importance measurement, including sharp values and sharp values interaction. Also, we have tree visualization functions, and we have tools for making ranking analysis. Also, CatBoost models could be easily integrated in your production, as we believe, because we are supporting lots of languages, and now we just are supported Nodejs, and we are preparing a release of CatBoost for Nodejs library on NPM. And let me just glancely talk about our plans. We want to solve some problems in CatBoost. One of the annoying problems is that there is some discrepancy in quality between CPU and GPU version, and we are trying to solve this case. We want to support GPU for Spark training. We want to make our library support for R better. We want to solve lots of persisting problems, and we want to make CatBoost available at CRAN, and also lots of different features. So I think we are out of the time, and I think we need to start a questions section.
Thank you, Stanislav. So let's see if there are any questions. And first question from Jordan: what is a classic example for when to use standard uncertainty versus knowledge uncertainty?
It's a great question, because currently it's a pretty experimental feature. For example, what is an example of data uncertainty? Inside in Yandex, we have our weather prediction service, Yandex Weather, and there is some noise in data. For example, some data provider can send us noisy temperature or noisy cloud hemisphere percentage values, or something like that. And we are currently experimenting with the data uncertainty prediction for those data. Also, there is lots of we've trained the uncertainty prediction models on some let me recall, some classic data sets like adults, I guess, where we're trying to predict the knowledge uncertainty of models. So I think it's kind of pretty experimental still, and we are only searching for practical usages of it. Or I don't correctly understand the question. What was the question?
So the question was, what is a classic example for when to use standard uncertainty versus knowledge uncertainty?
So yeah, and my question was really, I'm assuming a lot of times you want to try different approaches, obviously, and then see which one works the best in most cases. I was just curious what you found to work better in the past, or if it really just varies on the data set.
I think that the thing that works best is the combination of data uncertainty and knowledge uncertainty, because it gives you the total value, total uncertainty. And I think that it is the most important value. And I've remembered one practical example of total uncertainty usage. It is an active learning. When we have some model deployed in production and we have some data stream that goes through that model, and we use the objects with the most uncertain, most values of standard deviation, to send them to markup and to work out what's wrong with them.
Okay. All right. Thank you very much. That helped a lot.
All right. Next question from Norm. Could KS, I assume Kolmogorov of Smirnov, give some detail on the heuristics they use for hyperparameter default values?
Okay. What is the heuristics of that CatBoost uses inside? First of all, it's, as I've said, after learning rate estimation, and it uses the number of objects in dataset and number of iterations that you need to train. And as I remember, we use number of features, or let me recall it later. But we are using just a linear combination of those parameters, and we've used a set of data sets to tune that linear formula. Another kind of heuristics that we use inside of CatBoost is different types of leaf estimation algorithms that are used for different losses. We use mean gradient for ranking models. We use Newton leaf estimation for regression models. We use exact leaf estimation for quantile losses, and so on. Also, we are using different number of, for example, steps by the for the Newton leaf estimation algorithm for different data set sizes. Also, there is different bootstrap algorithms for GPU and CPU for different losses, and I think that it's pretty shady thing, because it's not the only parameters that we are using to substitute internally. And to look at them, you can use CatBoost method get all parameters in Python to get an actual set of parameters that that were used during the model training.
All right, Norm, we are honored to have you here. So feel free if you have more follow-up questions to this one. All right, otherwise, let's go to the next one from Dennis. XGBoost uses first and second order gradients to estimate loss change on a split. Do you use both too?
By default, we use only first derivatives to measure scores, and we are using a special score function. We named it cosine because we are just measuring cosine distance between the vector of gradient and the predicted values of leaves. And we are using just a simple first order gradient, first order derivatives to measure these scores because it's faster.
All right, next question from Mash. May I ask a non-ML question? And as I am also very curious of business aspects of open source development, CatBoost is super amazing. So what is the strategic commercial growth path for CatBoost?
It's a pretty good question because currently we are just doing that to, spread our technology and to spread knowledge about our company, about Yandex in the wild, to make it, more widely known. And we currently have no plans for commercial applications of CatBoost from our team, and it's mostly because the CatBoost is developed for using in production of Yandex, and the most time of on our job we are doing things for Yandex, and it's those nice features that goes to open source is just side effects of development them for Yandex.
All right, great, thanks. Next question from Jay Slam. He was the speaker last time. He's actually a core developer of LightGBM. Is there any plan to support Dask array for distributed training for those who want to use Python but not Spark?
Okay, it's a nice question. The short answer is no, because we just don't have resources to support it. But speaking about plans, of course, as the auditory or the users base of Dask rises, I think that we will look at it and support Dask training in CatBoost at some time. Because the Spark support was a really tough task, and here in this talk there is Andrew, who was developing the Apache Spark support for more than 1 year, and to build the bridges between C++, which is the main language of CatBoost, and Scala, which is the language of Spark. It's really tough. Yes. And I think that Dask could be easier, but we don't estimate it. Yes.
All right, great. It seems like, yeah, he says, thank you. It seems like we have no more question, and we are right in time, because I was planning to finish by 55. So if anyone has meetings at the hour, they can go. So thank you so much for doing this, for coming and talk to our meetup. And I think I talked a few times about GBMs at this meetup, and in my view, there are like 4 libraries that kind of are the most used: XGBoost, LightGBM, CatBoost, and H2O. And I'm happy to announce now that I already have secured for the next talk to to have a core developer from H2O coming to us. So then we'll have all the 4 main tools covered. So thank you so much. That's it for now. And
yes.
I'm going to announce on Twitter and all the other channels very soon the next meetup. So the next one will be on H2O. Thanks, Stanislav, again.
Yeah.
For,
Yes, join our Twitter. We are planning to post some tips and tricks here. Join our Telegram chats for support. And bye-bye. It was nice to speak here.
Awesome. Thanks again for talking here. Bye-bye.
Bye-bye.
Thank you very much.